Hi, I'm Coach Cowland, and in this presentation we're going to look at Newton's first law. So first, a bit of background about Sir Isaac Newton. So Isaac Newton came up with 3 laws of motion. These were to explain the astronomical observations of Galileo and Kepler. In addition to these, he also made several other contributions to science in areas such as optics and calculus. So first of all, what is a force? A force is a push or a pull on an object. Forces are what cause objects to accelerate. This means that they cause objects to speed up, slow down, and change direction. How do forces interact? Forces can interact in a number of ways. First, they can act directly on the object as a direct push or a pull. This is known as a contact force. If a force acts through a string or a wire, it's known as tension. If a force acts without any kind of contact at all, it's a field force. Gravity is an example of a field force. Newton's first law states, a body in motion stays in motion at constant velocity, and a body at rest stays at rest unless acted upon by a net external force. This is known as the law of inertia. In chemistry, we define mass by how much matter there is. In physics, we define mass by how much inertia something has, i.e., the more it resists moving, the more mass it has. Logically speaking, this actually makes a lot of sense. The more something resists motion, the harder it is to move, which means the more force you need to move it. You may be wondering what is meant by the term net force. The net force is the sum of all forces acting upon an object. The reason why we use the term net force is because often there are more than one forces acting on any object at any time. For example, on a moving car, you may experience air resistance, gravity, a normal force, and the push of the car engine simultaneously, while the net force on the car could be 0. So what are the implications of Newton's first law? If there is no net force on a body, it can't accelerate. This means that it won't change direction, it won't speed up, and it won't slow down. So let's look at an example where there is 0 net force. A physics book rests on a table. The force of gravity acts down on the book. Because the book is at rest and not accelerating, we know that there must be a counterforce. This means there must be a force from the table upwards onto the book to stop it from accelerating. Otherwise, the book would fall through the table. This means that both forces are balanced and the net force is equal to 0. Often, the words mass and weight are used interchangeably. They are not the same thing. The mass is the amount of inertia something has, while the weight is the force due to gravitational attraction on that mass. To calculate the weight, we multiply mass times gravity. Here's a sample problem. A man weighs 150 pounds on Earth at sea level. Calculate A, his mass in kilograms, and B, his weight in newtons. Pause the video and hit play when you're ready. First, his mass. 1 kilogram is equal to 2.2 pounds, so dividing 150 pounds by 2.2 gives us a value of approximately 68 kilograms to 2 significant figures. His weight is equal to his mass multiplied by acceleration due to gravity, which is 9.81. Multiplying 68 by 9.81 gives us a weight of 669 newtons. We show the forces that act on any body by using free body diagrams. We use vector arrows to represent the forces. The length of the arrow represents the magnitude of the force, and the direction of the arrow represents the direction of the force. Here is an example of a force diagram and a free body diagram for a book sitting on a table. The free body diagram is much more simplistic than a force diagram. Each force is labelled. Here's an opportunity for you to try one yourself. A monkey hangs in equilibrium by its tail from a tree branch. Draw a free body diagram representing all the forces on the monkey. Pause the video, hit play when you're ready. First, the force of gravity acts downwards on the monkey. To keep the monkey in equilibrium, the force of tension acts upwards through the tail. These are the only two forces acting on the monkey. Here's a slightly more complicated one. Now the monkey hangs in equilibrium by both hands from two vines. Each of the monkey's arms are at 45 degrees from the vertical. Draw a free body diagram representing all the forces on the monkey. Pause the video, hit play when you're ready. Again, the force of gravity acts downwards. The weight of the monkey hasn't changed. This time, the tension is divided between both arms that are at 45 degrees to the vertical. The vertical component of force A1 and A2 are equal to the force due to gravity. Okay, so that's the end of the presentation. So what I need you to do is go back through it, make notes on everything that we've covered, complete the examples, check that you understand them, write down any questions that you have, things that you would like to go over in class. I'd like you to think of at least 2, and be prepared to continue on working on this in class, and I will see you then. Goodbye.